Hello everyone and welcome to OneClass. My name is Jeff Krause and I have a PhD in chemistry. Today I'm going to run through a few undergraduate high school level chemistry questions. So here's our first one. So we have an H2O molecule that looks something like this, in which each of our bond lengths, which I'm going to write as ROH. So ROH is equal to 0.096 nanometers. And then the HOH bond angle, which I'm going to call theta, is equal to 104 degrees. And so it wants us to calculate the moment of inertia of the H2O molecule about an axis that passes through the center of the oxygen atom. And it wants us to calculate it first through an axis that I've shown here, where it just goes straight through and is perpendicular to the molecule. And so that's A. And B is an axis which passes through and bisects the bond. That doesn't really bisect the bond as I've drawn it there, but I wouldn't be able to draw it otherwise. So it should be equal on both sides for B. Okay, so first I'll redraw the axis each time. And maybe next time I'll get it a little better. So there's ROH. And there's theta. Okay, so our mode of inertia is just the sum over each of the atoms, and we take the mass and multiply it by the perpendicular distance squared. So the perpendicular distance to the axis. So for an axis which passes through the oxygen atom and is perpendicular to the molecule, so it's going into the page or out of the page, it doesn't matter, from this little dot. And so we can see that the R's for the hydrogens is just going to be equal to ROH, and the R for the oxygen is just going to be 0. And so our mode of inertia is just going to be mass of oxygen times R of oxygen squared plus where I've labeled H1 and H2. But of course it won't matter because RO is 0. RH1 is equal to RH2. The vector isn't the same, but the unsigned distance, which is what we need, is the same. So it's just equal to ROH, which is our 0.096 nanometers. And then the mass of hydrogen I'm just going to use as 1.00784 grams per mole. And so with these quantities, our mode of inertia, so because the RO is 0, that is just 0. And then because these are the same, it's just 2 times the mass of hydrogen times this distance squared. comes out to be 2 times 1.00784, which, if we punch it through our calculator here, comes out to, where did I put it? 0.0185765 grams per mole, nanometers squared. So typically a mode of inertia is in kilograms meters squared. So I'm just going to convert it. So to convert it from nanometers to meters, we need this factor. So there's 1 times 10 to the minus 9 meters per nanometer. And then to get rid of the mole, or actually convert the gram to kilograms, we also need to multiply by 1 times 10 to the minus 3 kilograms per gram. And then to get rid of the mole, we have to divide by Avogadro's number. So these are going to make this quantity very small. So 3.0847 times 10 to the minus 47 kilograms meters squared. Okay, so that's for the first part. That's for an axis perpendicular to the molecule. So part B just asks for an axis which bisects the angle, and I'm just going to try to draw that a little better than I did the first time. Okay, so that's pretty good. Okay, so again, we have our ROH. So now our mode of inertia is, well, still our mode of inertia is the sum of our masses times our perpendicular distance squared. So now our perpendicular distance to our hydrogens is this distance. Where that is still our angle, which means since it bisects the angle, that the angle in here is 52 degrees, as the full angle is 104, which makes this side over here, this would be sine, right? So I'm just going to redraw the triangle that I've got here, right? So this would be ROH, this would be 52 degrees, and so this would be ROH cos of 52 degrees. And this would be ROH sine of 52 degrees. Okay. Which is equal to 0.096 nanometers times the sine of 52. Which comes out to be 0.0756 nanometers. Okay, so our mode of inertia expression is still the same, so it's MO RO squared plus MH RH1 squared plus MH RH2 squared. Our O is still 0 because its perpendicular distance is still 0, so that goes to 0. And each of our RH's is the same. As the vectors are different, but the unsigned distance is still the same. It's just equal to this value now. So 2mH RH squared. So I'm just going to call this RH. So our mode of inertia is 2 times our mass of hydrogen, which is 1.00784 grams per mole, times this distance squared. Now if we run this through our calculator, this comes out to be 0.0155 grams per mole, nanometers squared. Again, I just want to convert it to kilograms meters squared because that's the typical units. So I just use 10 to the minus 9 meters per nanometer, 10 to the minus 3 kilograms per gram, and then we're going to divide the whole thing by Avogadro's number. And so this will cancel the moles, the nanometers, and the kilogram, or the grams, sorry. Leaving us with kilograms meters squared, which is 1.9155 times 10 to the minus 47 kilograms meters squared. And so there's our 2 moments of inertia. If we check through the solution, so for part A, we got 3.08 times 10 to the minus 47. I should have probably cut that at 2 significant figures. Is it 2? I'll have to double check. Yeah, so it should actually probably be 3.1. 3.1 times 10 to the minus 47. So it should be 3.1 times 10 to the minus 47 with 2 significant figures and 1.9 times 10 to the minus 47. But in any case, these values are consistent with the solution given here, so I would say this is correct. Okay. All right, so for our second question, it asks us to draw the Lewis structure and then answer a couple questions. So for SO2 Cl2, and the questions are just about hybridization and shape, I believe. Okay, so first of all, for SO2 Cl2, so our sulfur has six valence. Our oxygen has 6 valence times 2 oxygen atoms, so 12. And our chlorine has 7 valence times 2, which is 14. So in total we have 26 plus 6 is 32 valence. So we have 32 valence electrons right now. So let's try to put them all in around each other. So if we have sulfur in the middle, which in retrospect I should move a little lower. So sulfur in the middle. do not include overall ion charges, and do not include double bonds unless they are needed for the central atom to obey the octet rule. Okay. So without double bonds, or formal charges. Okay. So normally these guys would look like this, and sulfur would also be like this. Okay. So that's the typical valence around each of the atoms, and so we can get a bond here, a bond here. And now, unfortunately, the sulfur-oxygen bonds are not possible. As well, the oxygens wouldn't be filled. So I'm going to go ahead and just remove the electrons around sulfur. So we're 4 short, or at least just remove 2 of them. And I'm going to put them on the oxygens instead. And that will allow us to bond to oxygen. Now if we count up here, so we have 8 plus 8 is 16, plus 8 is 24, plus 8 is 32. So we've got all of our electrons in here. And then it doesn't want us to include formal charges in the drawing, but that's okay. I'm just still going to use formal charges just to check our work. So around the chlorine, we have 7. We expect 7, so that's formal charge 0. That's also a formal charge 0. Around the oxygen here, we have 7. We normally have 6, so that's a delta minus. This one's a delta minus. So far we have -2 charge. Around this sulfur, though, we have 4 electrons and normally expect 6, so this is a delta 2 plus. So in total we have a neutral molecule, so that's good, as it should be. Okay, so if we look at structure around the molecule, so if we drew this, it would look like this. Which has a tetrahedral geometry. So the electron geometry would be the geometry of the bonds around sulfur, which is also tetrahedral. So it's a tetrahedral electron geometry, as well as a tetrahedral molecular geometry. As in, the bonds or the electrons in the bonds have the same shape as the molecule or the atoms surrounding the sulfur. And I'm not sure what the other questions are. I believe that is the questions. Okay. So there's our Lewis structure. It says not to include formal charges, but all I have to do to not include formal charges is just erase them. And it's best to check formal charges, and the shape will be tetrahedral. Okay, so this looks good. Solution is correct. Okay, so this one is, so for the third question, wants us to draw the Lewis structure for XeCl4, show all lone pairs, identify the geometry, what are the approximate bond angles, and is it polar or non-polar. So for xenon, that's a noble gas, so we've got 8 valence, and then in chlorine we have 7, and there's 4 of them, so that's 28. So in total we have 36 valence. So each of the chlorine atoms will have 7. And xenon typically has 8. We obviously want to be able to bond to 4. And then that's 5, 6, 7, 8. We know xenon can become hypervalent, so I'm just going to add in the lone pairs kind of around it like that. And so obviously we can't really count xenon octet for xenon because this is an expanded octet. And so then there's our bonds. If we count everything up, there's 8, 16, 24, 32, plus 4 is 36. Okay. If we draw the molecular structure, it would look something like this, where the lone pairs I have going above and below xenon. And I'm using wedges and dashes to indicate a bond coming out of the page and into the page. And so this is a square planar molecule. So in Vesper theory, this would be either B2, AX4, or maybe A2, depending on what you want to call the lone pairs. And so this is a square planar molecule. So that's our geometry. Each of these bond angles in here would be 90 degrees, as it's 360 around the circle. So our bond angles are 90 degrees, and then this is a symmetric molecule, and that means it's non-polar, right? So each of the bond dipoles between chlorine and xenon will perfectly cancel, leaving you with a zero dipole. So non-polar, so the dipole is 0. I believe that's all the questions that are in there. Showing all lone pairs, identify the geometry, what are the approximate bond angles? Yeah, okay. So just checking to the solution here. So we get a square planar with bond angles of 90 degrees. Perfectly symmetric, so all the dipoles cancel, giving us a 0 dipole. So that looks good. All right, what is the equilibrium constant expression for the following reaction at 25 degrees Celsius? So copper 2 plus. And I'm just going to migrate this a little bit. Goes to copper solid plus silver plus aqueous. Okay, so this is a redox reaction. So what we have shown here to split it into the 2 half reactions is copper 2 plus 2 electrons goes to copper solid. So this would be the cathode reaction or the reduction. So this is the cathode, or the reduction. We know because it's consuming electrons, right? So electrons are on the reactant side. And we have 2 silver going to, that's not right, but 2 silver plus 2 electrons. So this is the anode side, or the site of oxidation. And we know that because it's producing electrons. So the silver is being oxidized, producing electrons, so this would be the anode side. Okay, so given these 2 half-cell reactions, we can look up the relevant statistics, so the reduction potentials for these, and compute our E0 cell, which is equal to our reduction potential so our standard reduction potential for the cathode minus the standard reduction potential for the anode. Okay. So if we look these up, we would get 0.34 volts for this guy and negative 0.80 volts for this guy. It's handy to remember that this is the value you would get for 1 silver, but we don't do anything to it for 2. So the standard reduction potential stays regardless of our stoichiometric coefficients. That'll be taken care of later. So our E0 cell is then 0.34 volts minus 0.80 volts. Oh, sorry. That would be plus 0.80. And so that should be plus, which makes it 0.46 volts. Okay. So that's our cell potential. And this is already our first clue that this reaction is in the wrong order. So if our E0 cell was positive, then the reaction would be spontaneous, it would flow. But because it's negative, it's actually going to flow in the opposite direction. But that's okay, we're going to compute the K regardless. So we can calculate our K from the Nernst equation, which is E0 cell is equal to RT over NF on K. So in this case, so RT and F are all constants. So R is our gas constant, which is 8.314 joules per mole Kelvin. F is Faraday's constant, which is 96,458 coulombs per mole. Our T is our temperature, which is 25 degrees Celsius given in the question, which is equal to 298.15 Kelvin. And then N is the number of moles of electrons transferred. So here is where I mentioned we don't do anything with our standard potentials, and it'll be taken care of later. This is the later. So we can see here that 2 electrons are transferred. So N is 2. Okay, so RT over F is equal to 0.0257 volts. So that's just putting these values through our calculator and doing appropriate cancellations of our units. So we can see that the moles will cancel, leaving us with joules per coulomb, which is a volt. And so our E naught cell, which we computed above as negative 0.46 volts, is equal to 0.0257 volts over 2 times ln K. With some rearrangement, we find that our ln K is 2 times negative 0.46 volts over 0.0257 volts. So the volts cancel, which is good because we want this to be unitless. And so this is negative 35.80. Or our K is 2.83 times 10 to the minus 16. So again, our K is showing us that the reaction doesn't flow this way. So that makes sense. Because our K is much, much less than 1, that means it favors the reactant side. So now we can check to the solution here. So the E naught for silver here is funny at negative 0.4, but then we can see in the calculation of the cell potential it's been fixed, so that's okay, giving us our E naught cell of negative 0.46 volts. So there's 2 electrons, so N is 2, okay. And then our K is going to be, so we can solve for our K, and they got 2.84, so pretty much the same, just a little bit of rounding differences. So it's okay. Just a small error on your oxidation potential. Okay, so that looks good. Okay, so the next one is my 5th question here, which is, what is the hybridization of bromine in BrF3? So first let's draw this out. So we've got 7 valence electrons for bromine, 7 for each fluorine times 3, which is 21. So in total we have 28 valence. Okay. So obviously we're going to have to be hypervalent here to fit 3 fluorines around bromine. So just going to place these down. And so we're going to need 3 bonding electrons, and then we need 4 more to fill in the 7. So that would be 2 lone pairs. And so now if we count this up, we've got 8, 16, 24, plus another 4 is 28. So there's all our valence, so that looks good. And so if we draw this guy, I'm going to put the lone pairs out here, coming out of the page, and into the page, and then our fluorines. I'll be doing this. So this is a T-shaped molecule. And now for counting up hybridization, we need to look at how many things are bound or bonded to the bromine. And in this case, we count the lone pairs. So for hybridization, you count the lone pairs. So that would be 1, 2, 3, 4, 5. And so 5 has to total our values that we use to put up top. So 1, 3, so 3 plus 1 is 4, plus 1 is 5. And we don't usually put the 1, we don't usually show the 1. So we would say that for bromine, we have an sp3d hybridization. Okay. Yeah. So an sp3d hybridization. Okay. To determine, we look at the Lewis structure, count the number of groups bound to bromine, so in this case 5, and then we just have to make those values sum to equal 5, so we get sp3d. So that looks good. Solution is correct. Okay. So for my next question, it says the RAST method uses CAMP4, which is C10H16O, to determine the molar mass of a compound based on freezing point depression. So when 2.50 grams of cortisone acetate are dissolved in 50 grams of camphor, the freezing point of the mixture is 173.44, and that of pure camphor is 178.40. And then it asks us to solve for the molar mass of cortisone acetate. So our freezing point depression equation is just our freezing point depression constant, Kf, times our molality of our solute, where our molality is in moles of solute over mass of solvent. So that's important. So this is in moles per kilogram. Okay. So typically expressed in moles per kilogram. So that would be the M here. So our Kf, or M, I should say. So the M in our Kf constant, so our Kf is given as 40.0 degrees Celsius per M, or 40.0 degrees Celsius per mole per kilogram. Okay? So, all right, so then our freezing point depression in this question is just 178.40 degrees Celsius minus 173.44. So that's how much our freezing point dropped by, which comes out to be 4.96 degrees Celsius. So we've dropped by 4.96. So then 4.96 degrees Celsius is equal to 40.0 times B. Where our B B is our moles of solute over our mass of solvent. So our mass of solvent is 50.00 grams, or putting into kilograms, 0.0 kilograms. Okay, so that's our mass of solvent in kilograms. So putting this into our freezing point, so putting this in for our B up here, we would get 4.96 degrees Celsius, and just doing some rearrangement. I'll just leave it. Mole per kilogram is equal to our N solute over our mass of solvent. All right. And so then we can solve for our moles of solute. Which is then just 4.96 degrees Celsius over 40.0. And so our degrees Celsius is going to cancel, and multiplied by our mass of our solvent. And of course this kilogram here is going to cancel with that. Oh, right, it's per. Yeah, okay. And then moles will actually pop out on top here. Okay. And so this comes out to be 0.00620 moles. Okay, so there's our moles of solute. And now it asks us for the molar mass of our solute. So the molar mass is equal to the mass over the molar mass. And so these will all be solute, as we're looking for the molar mass for our solute. Our mass is 2.50 grams, which is given in the question, over 0.00620 moles, which comes out to be 403.226 grams per mole. And rounding to our three significant figures, 403 grams per mole. Okay, so there's our molar mass for our cortisone acetate. If we check through the solution here, so we can use the freezing point depression equation, and we get 403.23 grams per mole, or rounded for significant figures, 403. So that looks good. Okay. All right, so for our seventh question here, calcium carbide contains the acetylide ion C22-. Sketch the molecular orbital energy level diagram for the ion and the electron dot structure. Okay, so in constructing molecular orbital diagrams for homonuclear diatomics, the biggest thing we need to remember is that our 2p orbitals have two options for how they overlap. So one way is to result in a sigma orbital, 2 pi orbitals here, 2 anti-bonding pi orbitals here, and a sigma orbital up top. which should be roughly equally displaced about the middle. So this would be a sigma, a pi star, and a sigma star. Or the two p orbitals could overlap to yield two pi orbitals downstairs, a sigma orbital, and then two pi orbitals and a sigma orbital. So pi, sigma, pi star, sigma star. And it does this depending on where we are in the periodic table. So the cutoff is here. So this side uses this one, and this side uses this one. So oxygen and fluorine will use this version, and carbon and nitrogen back will use this one, so the lower of the two. And since we're doing C2 2 minus, that means that we're going to use this version of our 2p overlap, or this molecular orbital diagram. Okay. So after that, now that that's taken care of, I'm just going to do the full MO diagram now. So our 2p orbitals, so for our carbon and our carbon, our 2p orbitals will be here, and our 2s will be here, and not to mess up any of the spacings. Okay. So we're going to get a couple, and like this, roughly like that. So we've got a sigma star, a pi, sigma, pi star, and sigma star, where the unstarred molecular orbitals are bonding and the starred are anti-bonding. Okay, so in carbon we would normally have 4 valence. And so then in C2, oops, what am I doing? What am I doing? All right, so then in C2, which is in the middle, we would have piling in all these electrons. That'd be 4, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that's C2, but then we need a -2 charge, so that's an extra 2 electrons. So then there is our molecular orbital structure for C2 2 minus. Okay, so we can see that if we do the bond order out, so our bond order is our number of bonding electrons minus our number of antibonding electrons all over 2. So if we count this up here, we have 2, 4, 6, 8 bonding electrons. And we have 2 antibonding divided by 2, 6 over 2, which equals 3. So we have a triple bond. So the questions, there's 5 questions asked in this question. There's 5 5 smaller questions. So the first is how many sigma bonds and pi bonds. So we can see here that we have 2 pi bonds and a sigma bond. So there's 1 sigma and 2 pi bonds. So that would be net as well, because this sigma bond is being canceled with this sigma antibond. So you just count the top ones, basically. Very similar to counting valence. The next question is the bond order, which I answered there. So our bond order is is 3. The next question is to compare valence bond theory with MO theory. So our valence, if we look at, say, our Lewis structure, right, where for C2 minus we need 4 times 2 equals 8 valence electrons, but then we need to add 2 for this, so we need 10 total. So we need to add a couple more, and then but then these 3 can give us our triple bond. So that would be C. So we would have a triple bond. So in both cases, we get a triple bond on our carbon, which corresponds to our bond order of 3. So valence bond theory and MO theory agree in this case. Okay, and for D, the question is, how does the bond order change in going from C2 to C2 minus? So if we look at our MO diagram, which I'm just going to re-sketch out, but just the top orbitals. So we have a pi, a sigma, a pi star, and a sigma star. And so this was C2. And we went to this with C2 minus. And so our bond order here is equal to 4 over 2, which equals 2. And our bond order here is 6 over 2, which equals 3. So we went from a double bond in C2 to a triple bond in C2 minus. And then the last question is it paramagnetic? And the answer is no. It's diamagnetic. And it's diamagnetic because all the electron spins are paired in our MO diagram. So we need unpaired spin for it to be paramagnetic. And so just to reiterate this, if we look at our MO diagram, all the spins of all the electrons are paired, and so it will be diamagnetic. Okay, So now if we look down through the solutions given, it's a triple bond, so there's 1 sigma 2 pi bonds. Our bond order can be computed with this equation, which comes out to be 3. For C, I don't know what they're answering there. Valence bond theory gives us 3. I don't know what they're saying there, but that's okay. So adding electrons increased the bond order. Specifically, we went from 2 to 3. And C2, 2 minus is diamagnetic since they're all paired. That looks good. All right. And now, next one. All right, so the oxyanion of nitrogen, which has the highest oxidation state, is the nitrate ion, so NO3 minus. And the corresponding oxyanion of phosphorus is PO4 minus. So PO4 minus is stable, and NO3 minus is stable. So as you can see, phosphorus has 4 oxygens around it, while here nitrogen only has 3. So the other thing is that NO4 3- is not stable, and PO3- is also not stable. And so we want to compare the bonding structure to look at why this would be the case. Okay. So for NO3, so first of all, let's look at NO3-. So we have 5 valence electrons here. We have 6 valence electrons times 3, which is 18. So that's 18 plus 5 is 24, but we can't forget the negative sign. 18 plus 5 is 23, but we can't forget the negative sign, so we get 24 valence. So you got N, O, O, O. Just putting in the typical valence here. And adding one more for fun, apparently. Yep, I just keep doing it. Okay. And then we do need to add in one more for the negative, so I'll just put it there. And it looks okay, except we've got unfilled valence for these guys. So then we might as well give one of the electrons to an oxygen to get a octet on 2 of the oxygens and a double bond to the other. And so now octet is satisfied everywhere. We've got a delta negative here, a delta negative here, and a delta positive. So the total charge will be negative, but the total charge will be -1, and our octet rule is satisfied everywhere. Okay. So then, and the other thing to point out here, especially for this question, is that our nitrogen is sp2 hybridized. And this double bond is being formed from the overlap of a 2p orbital with a 2p orbital. Or actually, just to emphasize this a bit more, this double bond is being formed from a nitrogen 2p orbital overlapping with an oxygen 2p orbital. Okay. And so already we can see why PO4 minus might be tricky. So PO3 minus, sorry. PO3 minus would be phosphorus, oxygen. So just drawing the same structure again. This, delta minus, delta positive. Oh, trying to draw the same structure, but failing. Okay, and so this double bond here would actually be a phosphorus 3p orbital overlapping with an oxygen 3p orbital. 2p orbital, sorry. And so because, just because that's where we have our electron density in phosphorus. So we're going to have significantly less overlap between a 3p and a 2p than we would a 2p and a 2p. And so this is going to significantly weaken this bond. To the point where this is actually quite reactive. Alternatively, we could draw this, especially because phosphorus can become hypervalent, as this structure. Where phosphorus now has 5 bonds, but that's okay. Phosphorus can deal with that. But then, of course, this would be a P3P overlapping with an oxygen 2P and a 3D overlapping with an oxygen 2P, which might be a little better, but still not perfect. Although the negative charge is now firmly on the oxygen. But either way, we do have this higher N overlap going on. Okay. And then, so now looking at PO4 minus. So in this case, we've got our phosphorus, our oxygens are going to surround it. Okay, and our phosphorus, I'm going to give 4 electrons. So how many do we need here? So we've got 5 valence, 6 times 4 equals 24. So that's 24 plus 5 is 29, and then it needs a 3 negative charge, so that's 32 total. I'm going to go ahead and give these guys their doubles. And I am missing one from phosphorus, so I'm going to give it to this guy here as well. And so that could be one potential structure, where here we've got a delta minus on each of the oxygens and a delta positive on the phosphorus. Okay. Or alternatively, we could pull that in and give us a structure like this, which is now resonance stabilized. because our phosphorus can become hypervalent. And so we've got 4 oxygen atoms surrounding it. We've got quite a bit of charge delocalization across the structure. But alternatively, we can split this around here like this, as phosphorus can become hypervalent, so it doesn't mind having 5 bonds. And although we have quite a bit of charge, there are also significant resonance structures here, right? So each of these can go up and down, leading to many resonance structures stabilizing the charge delocalization. Okay. And this double bond, even though this double bond would be fairly weak, as it's going to be a phosphorus 3D with an oxygen 2p, we've got lots of space to do this, and the charge delocalization will help to stabilize the structure. So for NO4 3- though, we're kind of stuck with this structure, as nitrogen doesn't really have access to the d orbitals. And so then we're stuck with this structure, which is heavily charge delocalized. So whether we've got a positive charge in the nitrogen and negative charges on each of the oxygens. So this structure is going to be not very stable and want to separate, especially with all this negative charge around the periphery. So all these oxygens are going to want to split, and we can't do this. We can't do this trick where we force nitrogen to become hypervalent, as we don't have access to those d orbitals, and so we won't have this charge delocalization, which we would see for PO4 3-. Okay, so just to sum up, NO3- is a stable structure in which we get, and I didn't mention this before, but this also gives us resonance structures, right? So each of these could become a double bond. So our NO3- can lead to charge delocalization, which gives us some stability as well. Our double bonds are overlaps between 2p orbitals on nitrogen and oxygen, which will give us favorable overlap. For PO3-, looking at the same structure, we would still end up with some stabilization due to resonance. But we would actually only get very minor delocalization across these 2 oxygens, across all 3 oxygens actually. But our double bonds are all going to be formed from n equals 3 orbital overlaps, with n equals 2 overlaps on the oxygen. So these are going to be much more significant, much weaker orbital overlaps, giving us much weaker double bonds and leading to a structure which falls apart much more readily, or is much more reactive. In the case of PO4 3-, the ability to become hypervalent allows for, even though the double bond might be weak, it does allow for heavy delocalization of charge across the structure. And although our 3D to 2p overlap isn't great, it's still better than nothing in this case. And NO4 3 minus, we can't access this hypervalent property for nitrogen, and so we've just got massive charge aggregation of the oxygens, which would cause quite a bit of repulsion and cause the molecule to fall apart. Okay. So now if we look at the solution, so the nitrogen is not large enough to accommodate all 4 oxygen atoms, so that's essentially what we are saying here. So in PO4 3 minus, we can form favorable overlap between 4 oxygen atoms, or there is a way to do it, and allows for some stability. In NO3 minus, so both of them have p orbitals of similar size, so both of them are 2p's. Well, in PO3 minus, it's a larger p orbital or a 3p orbital, so it's less effective. So I'd say the solution is correct, although a little incomplete. Okay, why is O2 paramagnetic? So for oxygen, our MO diagram is going to be the overlap between 2 oxygen atoms. So there's our 2p and our 2s. So this is 1 oxygen atom, and here is our other oxygen atom. So we're going to get sigma star, and in this case we get sigma pi sigma. We get a sigma star, sigma pi star, sigma. So this is the ordering of the levels for oxygen. It's good to remember that for oxygen and fluorine, this is what it looks like. But before oxygen, we actually flip the pi and the sigma levels. So it would be these 2 down here would be flipped for carbon and nitrogen. But we don't need to worry about that here because we're dealing with oxygen. So each oxygen atom has 6 valence. Okay. And so we can just take these 12 valence electrons and fill them in. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And so our bond order for oxygen is our number of bonding minus our number of antibonding. And this isn't really relevant to the question, but I'm doing it anyway. So our bonding is 2, 4, 6, 8. And our antibonding is 2, 3, 4. And this is all over 2, which is equal to 4 over 2, which equals 2. So it's a double bond for oxygen, as we already know. So that's good. But for the question, why is it paramagnetic? All we actually need to see are these electrons here. And so because we have unpaired electron spins, that means we've got a paramagnetic molecule. And that's all that matters. So if the spins are unpaired, then it's paramagnetic. If the spins are paired, then it's diamagnetic. So in this case, we have an unpaired spin there, and so it's paramagnetic. And so this is not true. Diamagnets have a bond order of 0, which is not true. In fact, in a question I just did for C2, 2-, that is diamagnetic, and the bond order was 3. So that's just false. Let's have all electron spins paired. Paramagnets have unpaired spins. O2 is paramagnetic due to the unpaired pi star electrons. The presence of unpaired electrons at antibonding pi orbital results in thus a paramagnetic molecule. So it is correct that it's due to the unpaired electrons, but that isn't what results in the non-zero bond order. Okay, so I'm just going to say it's incorrect, just because that's that. Okay. Okay, so what is A, the Lewis acid, and B, the Lewis base in this reaction? So Fe3 plus 6H2O goes to FeH2O 6, 3 plus aqueous. And I'm just going to move this down a smidge. Okay. Okay, so a Lewis acid. So I'm just going to redraw them. And I'm just going to draw one water molecule. So a Lewis acid is an electron acceptor. And a Lewis base is an electron donor. Okay, so in this case, our water is donating electron density to our iron. So then that makes this guy the Lewis base and this guy the Lewis acid. Right, so the water is donating electron density to the iron to form bonds to the iron atom. So that makes our Lewis acid Fe3 plus and our Lewis base H2O. So now if we check the solution here, so our Lewis acid is iron 3 plus, and our Lewis base is water. So our Lewis acid is an electron pair acceptor, Lewis base is a pair donor. That looks good. Okay. So now for this one, okay, sodium bicarbonate is the sodium salt of carbonic acid. So H2CO3 pKa is 6.37. Okay, So it asks which of the following substances will react significantly with sodium bicarbonate. So to answer this question, we just have to look at what we have in our solution. So with sodium bicarbonate, this is a salt, so we're going to get Na plus HCO3 minus, and it assumes in basically 100% yield. So our HCO3 is going to want to react to yield H2CO3 plus OH minus. And of course our H2CO3 is going to want to react to form HCO3 minus plus H3O plus, and our H3O plus is going to want to react to form water. So in the end, what we have here is an equilibrium, right, where this guy here is our conjugate acid. And so this, in solution, our sodium bicarbonate is going to reach some kind of static state between forming H3O plus from our H2CO3 and then yielding water through reaction with its own OH minus. So the only way we're going to get any kind of significant reaction is if we mix it with something more acidic than its conjugate acid. So more acidic means lower pKa. And if we look at the pKa of the substances shown here, which are acetone, 2,4-pentanedione, phenol, and acetic acid, or vinegar. And if anyone's ever mixed vinegar with baking soda, I'm sure we already know the answer to this. So acetic acid is a pKa of 4.76, and the others are much higher. So this will be the only substance to react significantly. And just to reiterate, it's because the pKa of acetic acid is lower than the pKa of its conjugate acid, of the salt's conjugate acid. Okay? If we check the solution, so only acetic acid will react significantly since it is the only stronger acid as compared to the conjugate acid. And stronger acids would have lower pKa values. So that looks good. And what do we have here? This one should be a quick one. So this would be my 12th question, and that's an 11. Okay, so copper metal has a density at 20 degrees Celsius of 8.92 grams per centimeters cubed, and at 100 degrees Celsius of 8.83. It wants us to calculate the change in volume if we're given a piece at 20 degrees Celsius, which is 10.0 centimeters cubed, and we heat it from 20 degrees Celsius to 100 degrees Celsius. Okay. So first of all, we can use that the density is the mass over the volume, and mass doesn't change as we heat it. So we can calculate the mass from our density at 20 degrees Celsius times our volume at 20 degrees Celsius. So 8.92 grams per centimeters cubed times our 10.0 centimeters cubed, which comes out to be 89.2 grams. And then now we can compute our volume at 100 degrees Celsius as the mass over our density, which is 89.2 grams over our density at 100 degrees, so 8.83 grams per centimeters cubed, which comes out to be 10.1 centimeters cubed. And so our change in our volume is our volume at 100 degrees Celsius minus our volume at 20 degrees Celsius, which is 10.1 minus 10.0, which is 0.1 centimeters cubed. So our change in volume in heating from 20 to 100 degrees Celsius is 0.1 centimeters cubed. So checking through our solution here. So we use our density equation to compute our mass, and then our density equation to compute our new volume, and then we can compute our change. So that would be, so that was good. Okay. And now for my last one here, I'm just going to do this one. So is SiF4 polar or non-polar? So we can draw up our structure here. So silicon will have 4 valence. Each of the fluorines will have 7. There's 4 of them. So that's 28. So we have a total of 32. So we're just going to set it up with regular valence and then correct afterward if needed. And this looks good. Our molecular structure would look like this. Where I'm using wedges to show that they're coming out of the page and dashes to show they're going into the page. And so this is a symmetric molecule, meaning all the dipoles would cancel. So even though there is a dipole from fluorine to the silicon, they would all perfectly cancel. And so, so this is a symmetric molecule. And so it's non-polar. And so that's because each of our little dipoles cancel. So our total dipole cancels, giving us a non-polar molecule. So each of the SiF bonds would have a dipole, but they would all cancel, giving us a net dipole of 0. So it's non-polar. So that looks good. I'm going to say that's correct. And I'm actually just going to stop it here, though, and say thank you all for listening. I hope you enjoyed listening and watching this. If you did, please subscribe to OneClass. If you would like to leave questions, please follow the comments below the video. This has been Jeff Krause for OneClass.